Okay, Ahmed. Well, now it's the time for the second session for today. So I am Ahmed Wagih, a postdoc researcher at Mechanics of Composites for Energy and Mobility at KAUST. This is the second time you see me during the workshop. I have the pleasure to be the chairman of this session, which is entitled Advancing Processing Through Models and Data. In this session, we will gain some knowledge about how advanced modeling and simulation can help for processing, manufacturing, and design of composites. Okay, so the first speaker in this session is Professor Suresh Advani, who is a professor of mechanical engineering and associate director of Center for Composite Materials at the University of Delaware. He will give us a talk on emerging role of process models and simulation in composite manufacturing. So the floor is yours now, Professor Suresh.
Thank you. Thank you for the introduction, and thank you for inviting me here. I know that we can't do this in person, but I guess this is the second best thing we can do. So I've attended some of the talks, and I have actually enjoyed watching them. And I know it's very difficult to keep the attention span when you're doing through this to Zoom, but I'll try to be brief and not put too much time into extra things here. So basically, today my goal is to show you how numerical simulations are slowly becoming more and more useful in manufacturing with one of the simulations that we have developed in over the last 25 years. So of course, I haven't done all this work. The real stars are the students and postdocs who have worked with me over the years. And so I want to first acknowledge that they are really the responsible people for this. Composites are everywhere, as we know. This is this group. I don't need to tell them that. And as the parts become more complex, the modeling and simulation becomes more useful. And so that's been the mission. So 30 years ago, people were just doing trial and error, and I thought, okay, we'll bring in some science base into it. We'll break the wall between trial and error and process simulations that will help put in the science base. The progress has been slow. I mean, even in 30 years, people are still struggling with using simulations. They still prefer trial and error. But as we move forward, hopefully, the big hurdle, which is the difficult to use and train issue, can be made easier, so that more people will use it in their in the actual manufacturing floor. So today I'm going to focus everything on liquid composite molding processes, because that's the simulation we have developed. But the same knowledge base and simulation base can be transferred to other processes. So I won't describe the processes in detail, except that in liquid molding composites, you have a fabric that is mostly stationary, and then you infuse or inject a resin into it, so that you make sure the complete fabric is vetted, all the pores are saturated, so you have zero voids. That's the goal. And it seems so simple, but as the part gets more and more complex, the issue becomes more and more important in terms of being able to model it. So the issues and challenges are, void saturation, where to place the injection and vent location, especially if you have a huge, um, part like a wind blade, for example, or a very complex part which has corners. Prototype development time. Every time you make a new part, you spend months trying to spend money on developing the prototype. And so it may be nice to kind of get rid of that and reduce that time. And how do we introduce process control? And the biggest one is the reliability and repeatability. How do we bring in reliability and repeatability into composites? And of course, these are some of the solutions here. if we integrate flow modeling in prototype design, so it becomes sort of part of that environment, we account for material and process variability in the design process, not only of the design of the component, but the design of the process itself. And one of the big things that's missing that is preventing people from using simulations is the material database. There's no material database, so people say, okay, I can use the simulation, but what property should I use? And then obviously, once the simulations get better, you can optimize the process, you can introduce process control. And of course, a lot of the people are now talking about how do we employ digital twins and machine learning tools in this whole manufacturing process. So I'll touch that at the end. Okay, so why do we need even a simulation? So usually when you close a mold, you cannot see inside. So you inject the resin, you wait for it to come out of the vent, then you open the mold, and then you say, oh no, there is a big void here. Okay, let's throw it apart, let's change the injection location. So a simulation will let you see inside as to how the flow is progressing, which you won't be able to see otherwise. So what do we need for the simulation? Okay, so we need to be able to have a numerical model and so some physics of the process, which we modeled as flow through porous media. And so we solve for the pressure field in a final element environment. We have some boundary conditions, no flow out of the mold, injection pressure or the flow rate here, which could vary with time. And then we track how the flow front moves in the process by applying just mass conservation and Darcy's law. And of course, that was in RTM. In WARTM, you need a 3D model because you have a distribution media through which the flow is going really fast. So you actually have a through thickness velocity profile. So you need to solve for the problem in 3D. Now, obviously, in this problem, we have developed a final element solution, which I'm not going to go through it in the detail. But basically, what you have is you discretize your domain. And what you do is the green points are where you apply the boundary conditions. The red are where there is already resin, and the blue is where the flow front is. So you solve the equation for the pressure, and then you use the fill factor approach, a control volume approach, to just move the fluid from one control volume to another, and then you update the fill factors. And that way, the ones that were between 0 and 1 will become 1, so your domain has increased, so you don't need to remesh. You just keep track of the fill factors, and wherever the fill factors are 1, you solve the pressure equation there. Wherever the fill factors are blue, you basically apply the boundary condition or the flow front condition there, and then you march forward in time. And of course, the problem here is the permeabilities, right? These are material properties that we need the database for. And so, we have developed a setup where you can actually measure all the three-dimensional permeability values for any fabric. And then we can, create a database where different fabrics permeability can be logged in. So when people are doing the simulations and they know what type of fabric they're using, they can use those permeability values. Of course, this is by no way complete, but this is what one needs to happen for us to be able to use the simulation in an effective way. So basically, we created the simulation to make it easy for people to use. So you put in your permeability, you put in your CAD design, and if you have any draping issues near the corners, you can add those to it. And the output is going to be basically equal to the flow fronts, the pressure, and if you are solving for the temperature and how much the toes are getting saturated. So that's the output you get. Um, and we've validated over the years, and Darcy's law works fabulously well. This is a three foot by 2 foot part, and you can see how the flow fronts match very nicely. And so, originally this was used in when we first developed it in just trying to figure out where to put the gate, where to put the vent, how to optimize the gate. And then as we progressed, we started using simulation as a part of the design process, integrating it with the design process. And then we said, okay, we can also, if there is variability, we can introduce process control and optimization. So we can use it over there. And then eventually I'll talk about how machine design comes into the picture here. So this is just showing you very quickly as to how um, you can actually do very let me just change this into an arrow so I can play um, the simulation. So you can see that this was a helicopter keel beam part that we could simulate flow inside it nearly 2 decades ago. So we could do that. That was not the issue of the simulation. But this allowed you to see how the flow was taking place, and you can change your gate and vent location and so forth. And then the question came up, okay, which is, where should we put the gate? If I'm trying to make a part like this, I want no voids, I want minimum fill time, I don't want to use very high pressures. And so, you can do in the simulation, you can set up the gate at every node, rerun the simulation, find out the fill time and so forth in the background, and then you could do it at every node. So if you had 5,000 nodes, you'll need 5,000 simulations. So then we came up with some techniques such as branch and bound method, which allowed you to narrow down the number of simulations you would have to run and get the same answer. So we used the branch and bound method, which within 57 simulations, you could find the best gate location, or you could use genetic algorithms to find nearly the best location so you don't get trapped into local minimas, or you can do brute force, which will require 3,370. And now, of course, this gets out of hand if you have two gates you want to choose, because then it'll be 3,300 times 3,300, which will be a million simulation. So that's why you need some of these techniques. So, that was the early part, but then the issue started cropping up that, the reliability, this permeability in the mold may not be the same everywhere. It may not be homogeneous. So, it may change from part to part. So how do we address that? And so the solution is to design a robust process to account for part to part variability. We could use passive control, or we could use active control. So how do we do that? So first of all, what causes this permeability variation? So when you put a fabric inside the mold, you may have race tracking along the edges, you may have a little ply drop off, you may have a ribs cut short, you may have a corner. All these cause issues such as the resin will race very quickly through there. And even if you have a simulation that shows perfectly well what happens when there is no race tracking, it's not much help, because as you can see here, the simulation with no race tracking said, oh, put the vent in the middle here. But what ended up happening was, because there was race tracking, the resin went around it and the vent was over here. And even if you allow the resin to bleed out of the vent, eventually you can't get rid of this void. So, the race tracking does cause problems that one needs to address. And here you can see in a 3D part, the same thing, where the race tracking came on the left-hand side, so you ended up getting a dry spot on this side, on the right-hand side. Um, so, around corners, you can see, and we have validated that if you put a race tracking edge in a simulation, we can predict what happens basically in the actual mold. So it is possible to put race tracking edges and then predict what happens to the flow. For example, here you can see a part with the well wheels where, if you don't have any race tracking around the well wheels, the part will fill nicely and you'll have vents at the two ends. But if you do have race tracking around these black edges, which is the well wheel where you didn't put the fabric properly, then the resin arrives at the vents before it goes in that white area. So the white area will be where your void will get trapped, and that is because of the race tracking that happened along the wheel wells. So, so we said, okay, let's see if we can characterize race tracking at each edge. So had some of the students do the same experiment 5 times, 10 times, 5 students around, and we measured race tracking along the edges. And the answer was, even the same student couldn't get the race tracking in the same experiment that he did 10 times. The race tracking strength, is how many times the flow is faster on the edge compared to the bulk preform, varied from one part to the next, varied from one edge to the next, and varied from one student to the next. So the bottom line was, we cannot get rid of race tracking. So we really have to start accounting for this non-repeatable race tracking in our design process. So what we did was, we said, okay, let's create all the simulation when there is no race tracking, when there is some race tracking, when there is a lot of race tracking along one edge, along both edges, all the permutation combinations. And then we design our process based on all the permutations and combinations. And then once we do that, then we look at the likelihood of each scenario based on the data that is coming in from the manufacturing floor. We superimpose that on top of each other. And after we superimpose this, we find out where is the most likely place where the resin will arrive last. And then we put our vents over there. Like in this case, it's these two yellow areas. So that's where we will put the vents. And so, of course, we won't get 100% filling every time, but at least most of the time you'll be able to do that. So here is an example of that. So the example basically shows here that if you had these two if you had a gate and these two windows, and if you had race tracking along the windows, and you had some probability of how much race tracking will take place, that most of the time there will be less race tracking, some of the time there will be high race tracking. So you have all those scenarios, and then you can create about 10,024 scenarios, assuming there are 4 levels of race tracking along each edge. And then if you did an intuitive design, you would put a vent. If you had 3 vents, you'll put one here, and one at the end. And then you ran 1,000 simulations with random scenarios. You only succeed 28% of the time. If you use the approach I said, where you superimpose and take the probabilities, it says you should put the vents this way, which is completely non-intuitive. But then your success rate increases from 28% to 69%. So at least you double your success rate, but you still have a lot of wastage because, for 31% of the time, you're not producing a good part out of the 1,000 parts. So in order to increase that, what we really need to do is introduce active, approach for sensors with sensors and simulation, so that you can detect which scenario is taking place, and then you have a control action that will counteract that disturbance and give you a good part. And so, you have to put sensors in the mold. You could have a point sensor, or you can have a linear sensor or a smart sensor. And these sensors are very, very easy to understand. Basically, you have these two wires, and when the resin reaches in between them, the resistance goes from infinite to finite, and the resin has arrived there. So you can use that. So here's an example. So here what you have is you could either have strong race tracking or weak race tracking along this window. So there are 5 possible edges where the race tracking could take place, R1 to R5. So basically you have 5 edges, and you have either weak or strong. So you have 5 to the power of 2, 32 cases. So what you do is you run in the simulation all the 32 cases. You figure out where to put the sensors. So very early in the process, I can find out where the race tracking is taking place. And then I have a customized control action for that race tracking situation. I do this offline. I create a detection database. I create a control database. And then in my LabVIEW program, I have those all available in the experiment, so that when the sensors detect which scenario is taking place, the required control action will be put into practice. So you can do that by having some additional gates, some additional vents in the mold that you can close and open at every time you want. So here is a scenario when scenario 29 is taking place. If you don't have any control action, what's going to happen is when the resin reaches the vent, basically you're going to have this part which is not going to get filled. Now, if you use the control action algorithm where there is no intervention, the computer controls this, it detects which control action is necessary based on the sensor data. And in this case, you can see the left-hand side is the actual experiment, the right-hand side is the simulation. And what it says is open the gate on the right and drive the resin towards the vent, which is in the middle. So you can do things like that. Now, of course, you can do this in Wartum as well. In Wartum, you cannot apply positive pressure, but what you can do is you can have a vacuum chamber which will increase the permeability in certain zones and attract the resin to go there. So when you know that, so you built a gantry system with a camera, the camera can see whether the preform is not wet, and then it will tell the chamber to go there and suck the resin over there, because you can increase the permeability in that area. And we coupled this with our simulation. So we were doing this online. And here is an example when, as you see, there will be race tracking on the left and right. And as the resin is on the left, it goes to the right. And this is all automatic. And then you can use this with a robot to actually drive the resin where you want to, based on the simulation data. So, we found that this using the long range control gave us practically zero voids, the adaptive control. So now the last part of my talk in the last 5 minutes is about machine learning and digital twins, which, I mean, what we were doing was like a digital twin already, but how do we incorporate these concepts into the shop floor? So one example I want to present to you, but this can be expanded to many other examples. So for example, when you put a distribution media on the top, many preforms have these pinholes that you can see in here. So what happens is the resin from the pinholes will come down sooner and then create. So the resin is coming from the left to the right. On the top is the distribution media. You're looking at the bottom. So in the bottom, you can see that, in certain areas, the resin has actually come out of the pinholes here and trapping a void here. So these pinholes have an effect of how your part is going to form. And so the question was, can we characterize this fabric so then we can tell the fabric maker this is not good enough or this is very good? So what you do is you take a binary image and then you can see the pinholes. You can, where the light is coming from. And then this is 205 by 205 binary image. And then what on the right-hand side is a Moron's index, which tells you it's a 5 millimeter by 5 millimeter square, because that's how the toes are separated from. And if any toe has one pinhole, it will be a white region. If it doesn't have any pinhole, it will be a black region. And so this is the way to see what is the correlation between the different pinholes. So you have these two parameters, pinhole property alpha and the Moron's index I, which will characterize this fabric. So we can see that, if you do that, you get a kind of an alpha, which shows that, how the permeability is changing. And higher the alpha value, more spread out are the pinholes, the bigger are the pinholes. Okay. And then Moron's index tells you the correlation. So if there is no correlation, you are a Moron's index of 0. If there is some high connectivity or correlation, then you are at 0.5. And so what you do is in the simulation, you can run these, you can create a lot of data by running these simulations for different type of pinholes. And we can create, like for alpha equal to 1, alpha equal to 0.3, and Moron's index equal to 0.5, you can see that how the void fraction, what is the fraction of the voids you can get. And we varied alpha, we varied Moron's index, and then we saw, like what will be the standard deviation in these cases. So the goal would be that we already have this part, but how do we identify alpha and the Moron's index in this range? So basically, this is where the machine learning method comes in. You take the unsupervised learning, embed the original data in higher dimensions, and create a lower dimensionality. And there are two methods to do this, the PCA method or the SNE method. And so we use those and basically applied that to the fabric. And we converted 40,000 pieces of data and 400 pieces of data into much lower dimensionality. And the way we do that is there is a training step. We took 450 training samples. We ran it through a fast Fourier transform, the PCA analysis, and we created a 3D representation for alpha and the Moron's index. And then in the testing sample, you take the fabric that comes in from your fabric maker, and then you figure out what is the alpha and Moron's index for that. By comparing it to the data matrix that you have. And so this is the training step data that you've created. What happens in the lower dimensionality is that they bunch up together. So you can see that for alpha equal to 1, 2, and 4, for all those combinations, they sort of bunch up together. And so this is the training step that has created this for you. So now, and this is for the Moron's index, the training step. And now you can take your test sample and then you run your test sample through that and you see, okay, this is the value I get for my test sample. So the alpha value is going to be here for that, and the Moron's index is going to be over here. So I have identified immediately what those things are, which tells me that, okay, for those values, if I use these different distribution medias, this is the void fraction I'm going to get. So basically, it allows you to identify all those parameters, and you can that way characterize a fabric, what kind of variability is going to introduce into your process. And if it's going to be too much, you can send it back to the manufacturer and say, I want a much tighter fabric so that I don't get many voids. And so that's another place where you can use the simulation. So basically, the role of simulation is expanding. It started with, okay, here is what you want your vent and your injection to be. Then once you have different variations, how do you address that so that in the end you get a good part, as it was said yesterday, that you get the part right every time. And one could then put this into an automated manufacturing setup where all the variabilities will be handled, by the process. So I will stop here as my 25 minutes are up, and I will invite any questions anybody has. I know there are some questions that have been posted, but I will let the uh,
Thank you
I'll,
very
yeah. Thank you very much.
much for the nice talk. Yeah, just on time. Thank you. Yeah, we have a couple of questions Q&A. The first question, he asked about, is your solution based on finite element or control volume?
Okay, so it has both issues. The pressure is solved using finite elements. And then when we advance the fluid from one volume to another, we use the control volume approach. So it's called as finite element control volume approach.
Yeah, so you use both. Thank you. The second question, well, could you please comment on LIMS versus PM and RTM method?
Yeah, so LIMS is our code, which is also commercially available through the university. PAM RTM is a commercial company that does, they in addition to this, they do other things. And basically, LIMS is also used by many universities. So it's more like it can be used for research because it has a lot of external things that you can do with it that allows you to change and modify the conditions that you can do with. So we have done a lot of those things with other universities on that, and it doesn't have as good as interface as PAM RTM, but it does it is much faster. So you can do things like optimization and control, and for example, if you wanted to use it for machine learning, you can generate a lot of data very quickly.
Yep. Okay. Thank you. Yeah, we have two panelists asked to ask questions. So please, Muhammad, go ahead.
Thank you, Doctor, for your presentation. It was quite interesting, actually. I do have a question here. Have you looked at the effect of of the viscosity of the injection of that resin liquid? Whether it's going to change its property if the temperature changes, how it's going to behave? Is it more like Newtonian or not Newtonian? I'm just going to address all the question, and then maybe you can answer one by one.
I might forget all your questions, so let me answer one question.
Yes. Okay. Yeah. Take
so,
it.
The basically the viscosity easy question is that basically viscosity can be if you have a pot in which you have your resin where the viscosity is changing with time because of the curing. That's very easy to implement. We just let the viscosity be a function of time, and at each time step we update the viscosity. If your viscosity is changing because you have a non-isothermal process, then you have to solve the temperature and the flow equations together simultaneously, and then you can update the viscosity. We always use the Newtonian case. In the past, if you look at the literature, we have addressed non-Newtonian fluid cases, but here the flow rates are so slow that we don't expect many shear thinning effects, and most of the time you use thermosets, so that's not a problem.
Okay, thank you. Yeah, the last question is the nozzle type is used. Is it, but based on the answer that you gave me, it says it's a laminar flow, right? I'm assuming that you do the injection.
Yes, it's always
Yeah.
laminar flow in these
Yeah.
flows.
So the last one is the LIM code is compatible with most of the commercial CFDs software or not?
Yeah, I mean it has a DLL interface, so you can tie the DLL with MATLAB, or you can do it with other codes, and you can embed this code and call it as a subroutine from other codes if you wanted to. And also it interfaces with the CAD software, so you can import the geometry that you need, because geometry is an input. So
Thank you very much.
Thanks.
Appreciate
Okay. So we have one last question from Gilles. Can you?
Thank you very much, Ahmed. Thank you very much, Professor Advani, for your nice presentation. I have a question about when you make the real-time control. All the simulations are real-time, or you are using a kind of database of pre-simulated configuration, and then you try to get the one that is the closest to what you observe with the sensors.
So the first thing that I showed for that triangular, where it had a triangular insert mold, that was all done offline. And then all the, there was for each, the sensors would detect what race tracking scenario was taking place. And then that would, have a specified customized action. So it will just pick that and apply that in the mold. So that was offline. You create the whole database and then you apply it. Then in the part, we were actually able to do it online. So the camera would see what was happening. It will take that flow front information to the simulation. The simulation will then take that as the initial step and then change certain parameters to see what should be the next step. But it could only run like 3 or 4 steps. And then from that, it will choose the best possible step and provide that information to the vacuum chamber, and the vacuum chamber will then go to a different location based on that result. So that was done online. Basically, we hooked it up with the experimental part.
Okay, so that means real time you have the simulation plus the optimization of different configurations resulting of the location of the perturbation and everything.
Correct.
Okay. Okay, thank you.
Well, thank you very much for the interesting discussion. So Professor Suresh, you have still a couple of questions in Q&A. If you can address them by writing, it could be good.
Okay.
Reply them just now or whenever you prefer.
Yeah, I mean, there's somebody's asking about pressure sensors for controlling. No, we did not use pressure sensors. There were resin arrival sensors, but you can use pressure sensors because when the resin arrives there, you'll know the pressure will change. And so that's another way of doing it. The other question was the temperature of the mold has risen, will it affect?
Yeah, because the time now is running. You can write
Okay,
down.
sorry. Okay, I'll answer the rest in the
Thank you.
email. Yeah. Thank you very much. Bye.